Professor, yeah, I tried to solve this one, the volume, number 5, but I got negative 500 by...
Oh, if you know you got a negative number and you are talking about water, you are in the wrong business.
Where's my wallet?
Yeah, so this is what I got, I don't know why.
Which one is it?
I have that bad day. I'll be like, oh, it's negative. And like, so, maybe what I'm going to do is that, messing around with my PRA plus C silver that. So you want you saying we can do a software overclock? No. It's
Let me just take over the
you have to replace resistors. It's a bit of it's a long. Yeah, exactly.
So what you want to do here is you have a function, and you look at that function between A and B, and you look at that shaded area there, and you want to rotate it about the y-axis. You will create a volume. There are other ways to do this. You could try to change your x's and y's and make this your the axis. And I will tell you, good luck with that. It is quite a mess. It is quite hairy and quite, in general, quite difficult. That is to say, if you're rotating about the y-axis, you want to change the problem so that it's a matter of rotating about this axis. It is quite, in general, sometimes you can do it, it's quite easy, but generally it's quite difficult. When you take this curve and rotate it about the x-axis, you look at these elements, which is a slice. And you take the slice and rotate it here. You pick up a disk, and then you find the volume of that disk, and then you add them all up. And then you take the limit as delta x goes to 0. Now when you rotate this thing about this axis, it's a lot different. You may think it's simple. In many ways it's very different. Now what we have here is, if you want to look at this thing that you are trying to find the volume of, you are picking up a stadium. So say if you rotate it about this axis here, you take this curve, and you rotate it here, you have what looks like a stadium. You want to know how much of concrete to make that stadium, the volume of that stadium. So you will say, well, how do we do this by integration? By setting it up as an integral. Of course, you will say to yourself, why don't you just make an element and take that element and rotate it and find its volume, and then just do that with all the elements. That's your delta x over here. Then when you do that, you will notice the thing you will pick up is a shaft. You take this point and you rotate it about the y-axis. You want to pick up a shaft. You will say to yourself, what is the volume of that shell? And then just add them all up. You will get an approximation if your shell has a finite thickness. And if you want to get the exact answer, you will say, well, add them all up, but let the thickness go to 0. That is to say, set it up as an integral now. To do that, we need to know how to find the volume of a shell. Does anybody know how to find the volume of a shell? Well, you just use cylinders and say, well, take the volume of the inner cylinder, sorry, take the volume of the outer cylinder, drill a hole through it, find the volume of that thing, and subtract. So of course you're going to need the height. You're going to need the height. You're going to need the inner radius. And you're going to need the outer radius. What would be the outer radius? A little more than R. What's a little more than R?
B.
R plus something. Anybody know R plus something? Huh?
R plus B minus A.
R plus delta X. That's the outer radius. And we all know how to find the volume of a cylinder. You say pi r squared h. So you find the volume of the outer cylinder, you'll do pi that squared h. Find the volume of the inner cylinder, you'll say pi that squared h. So the volume of your shell who does not understand that? If you want, I'll take the pi and the h out, factor. It's r plus delta x squared minus r squared. You will now need to square this, and do not tell me that this is r squared plus delta x squared. If you want to square r plus delta x squared, you'll have to do r plus delta x and r plus delta x. Which is r squared plus 2r delta x plus delta x squared minus r squared. This is math 99 algebra.
So are the r squareds always going to cancel each other out?
Well, in this case, yes. The volume of your shell, pi h 2r delta x plus delta x squared. So this is the volume of your shell. If you have a radius r as the inner radius, and a radius of r plus delta x as your outer radius. That would be the volume of your shell and the height of your shell. Now, delta x is something that's kind of small. Which is to say, that if delta x is 0.1, delta x squared would be 0.01. If delta x was 0.01, delta x squared would be 0.0001. That is to say, delta x squared is kind of small. So that you can approximate this. Approximate pi h times 2r delta x would be the volume of this shell approximately. And now you need to add them all up. You need to add them all up. So I need this. Do my elemental analysis. And then to add them all up. And to let the delta x go to 0. The volume of my shell. Pi R H delta x. 2 pi times this R times this H times this delta x. So now we're going to come and look at this element here and see what's going on. You have a shell, you have a radius on the outer side, you have a radius on the inner side, and you have a height. So you can approximate the volume of this thing. Function f of x. What we're going to do is we're going to look at this element and create a shell out of it by rotating that element